Welcome to Module 38 of Database Management Systems course in the IIT Madras Online BSc program. We have been discussing about simple data structures in order to prepare ourselves for how the storage and data management in the physical layer would be done. In the previous module, we have talked about linear data structures, the common ones that we are always familiar with, array, list, and built on them are stack, queue, etc. We have also looked at what are the different options of searching a key in such data structures. Now, in this module, we will go on to nonlinear data structures, graph, tree, hash table, and so on. And we will specifically explore binary search trees. And at the end, we will compare the linear and nonlinear data structures. So these are the three main topics as you see on the left. So this is just to quickly recap. A data structure specifies a way of organizing and storing in-memory data. I emphasize that. And it enables efficient access and modification of the data. And efficiency is measured as a combination of time, which is primarily the access, but we also consider the efficiency of space. We have talked about the linear data structure. It is time for the nonlinear data structure. Remember that all data structure, at least most of them, have a container for the data which they are going to structure and manage, and a typical operation that needs to be done, and it is with respect to these operations that we want to measure the time efficiency and the space. And operations typically include create, insert, delete, find, access, close, and so on. Now, coming to nonlinear data structure, let us recall that from our study of linear data structure that all of them that we have seen in that array and linked list, ordered and unordered, all of them have the same space complexity, which is order n, and which kind of is optimal. However, we should always note that the actual space used may be lower in an array because there may be unused space, while in linked list there is an overhead of 100%. Because with every data node, you will have to keep a pointer. In the order it is 100%. In reality, it may not be so because the data node may be much larger than the pointer itself. So all of them also have complexities which are identical. This is incidental. This is just an observation. Incidentally, all of them have respective complexities of operations which are identical between the worst case and the average case. So we can just talk about one type of case. And all of them offer satisfactory complexity, maybe very good complexity for some operations, while they are very unsatisfactory for others. So this is a summarization table for it. So looking at the four primary operations that we would typically need in a database application, we can see that in terms of an array, the access is good, while in terms of a linked list, it is not. Insert, delete is really bad for arrays, and they are excellent for linked list. And search is kind of bad for everyone, except if I have an ordered array where I can do a binary search. So it clearly says that neither I can use array efficiently for all operations, nor I can use linked list. So we have to go to a nonlinear structure where we trade off between these extreme and kind of work out a moderate good for each and every operation. A nonlinear data structure, as the name suggests, does not organize the data in a linear sequence. Rather, it is a kind of a networked structure where the data elements are kind of organized through their linkages, and those linkages may not be as simple as a linked list like previous and next element kind of, but they could be different kind of hierarchical linkages that may be possible, and there may be more than one path to reach one element from another element and so on. There are several nonlinear data structures, but I will mention about the few major ones. One is graph, which could be undirected, directed, and so on. We'll talk a little bit more about that. The tree, which is going to be a mainstay for us in this discussion in the database applications, which could be of varied kinds as well. Hash table, which is also heavily used in database applications, and we will dedicate a separate module for discussing that. And some other ones like skip list, which we will not discuss here, but it's very interesting that it has multiple linked lists in a layered interconnected fashion and gives you very interesting performance measures. Now, coming to the specifics, a graph is basically a collection of nodes and edges between them. So, mathematically, graph is a doublet which has a set of vertices and a set of edges, so that the set of edges are pairwise tuples of the vertices, and there is an example of a undirected unweighted graph. Now, a graph could be undirected or directed, that is the order of the two vertices in the tuple may not or may matter. It could be unweighted or weighted. If it is unweighted, all weights are considered to be same and 1. It could have cycle or it may not have cycle, it may be connected or disconnected, and so on, several properties. And graph occur very predominantly everywhere. For example, we have seen a major application of graph in terms of the ER diagram. Every ER diagram is actually a graph, and there interestingly actually you have more than one type of node. Nodes also have different types. But simpler graphs could be different networks like electrical, water, sanitation, these kind of networks. Even there could be conceptual graphs like friendships in Facebook, the knowledge graph, and so on and so forth. So, it's a wide variety of applications to which the graph as a nonlinear structure can cater to. Tree, on the other hand, is very handy. It is a special type of graph which is connected. There are two major factors in this. One is it is connected, and then it is acyclic. That is, there is no cycle. It is connected. Every node should be reachable from the other, but it does not have a cycle. So, it kind of represents a hierarchical relationship, particularly if we have a root for it. It is not necessary for a tree to have a root. I mean, I can have a tree like this. This is a tree, but I have not identified what is the root. So, identifying root is an additional property, but usually we do that. So, it could be rooted or unrooted, it could be binary or n-ary, that depends on how many neighbors, what is the bound on the number of neighbors a particular vertex may have. If that bound is 3, 2 child and 1 parent, then we say it is a binary node, binary tree. Otherwise, it could be a n-ary tree for anything. It could be balanced or unbalanced. We will have to look into this property a little bit more. And I said that by definition trees are connected, but often times we also deal with forest, which is a collection of trees which are not connected between themselves. So, it could be, I mean, that kind of a collection of trees is called a forest. We will often need a forest as well. Now, for example, when we represented composite attributes, name composed of first name, middle name, last name, then we were talking about a tree. When we talked about date time, a date time is a day, a month, a year. So, these are different examples of tree. The family tree, we all know of the genealogy, search trees and so on. We will see a lot more of this. Now, since we will use tree heavily, I would like to introduce some definitions which I am sure from your algorithms course, data structure course you would know, but just a quick recap. The root is a node which is identified not to have a parent, and we will assume, at least in our discussion, that there is a unique root for every tree we deal with. The parent of a node is a predecessor in the tree starting from the root, and every node has a unique parent. The child are the nodes that follow a particular node. So, for B, these are the children, and for D, this is the parent. For E, this is the parent. So, the child could be many. So, from a node to the children, it is a one-to-many relationship, but a parent would always be unique. And a node which does not have any child is known as a leaf node. So, simple definitions you all would know. Then anything which is not a leaf node will be called an internal node. So, this is an internal node, this is an internal node, this is an internal node, but these are not internal nodes because these are leaf nodes. So, internal node will have at least one child. Then you say a subtree is one which is the tree rooted at some node which is not the root. So, this is a subtree of rooted at B. This is a subtree rooted at G. This is a subtree rooted at H which has only one node, right. So, that is the concept of a subtree, the entire thing hanging from that point. A path is a sequence of nodes following the edges. Typically, paths will be from root to some node, but it could be that I could also talk about a path which is I, E, B, A, G, C, G. This also actually is a path. Siblings are nodes which have the common parent, and arity is the number of children of a node. So, B has an arity 3, C has an arity 2 and so on, and a leaf node can be defined differently as saying that it has arity 0, and the maximum arity of a node that exists in the tree is known as the arity of the tree. So, you can say that for this tree the arity of the tree is 3, because this is the B which has 3 children, it has arity 3. So, this is a ternary tree, right. And it is not necessary for a n-ary tree that all nodes must have n children. Then we talk about level by identifying that the root is the root. So, it is at level 0. Then the children of the root are said to be in level 1. The grandchildren take up level 2. Great grandchildren take up level 3 and so on. So, level by level you could define a tree, and that becomes very important in terms of several analysis that we need to do. So, we say the height of a tree is the maximum level in a tree. So, here the maximum level is 3. So, we will say height is 3. In other words, the height, if I take a start from the root and start going down till I reach a leaf node, or till I reach a node, the number of links I cover is the level of that node. So, when I go from A to F, I go 1, I go 2. So, F has a level which is 2. So, in this way you can also define that the height is those leaf nodes which has the longest path from the root to that leaf node, right. Typically, we will deal with binary trees which have maximum of 2 children at a node. Now, there are few facts which I present without direct proof. If you do not know, you can always look up workout or always look up the book. One is a tree with n nodes have exactly n minus 1 edges. Does not matter what is the arity, does not matter whether it is rooted or unrooted, it will have to have n minus 1 edges. You can try to prove that. Now, maximum number of nodes at the level L of a binary tree is 2 to the power L. Why is it so? Because at 0 you will have one node 2 to the power 0. Now, this may have maximum of 2 children. So, you will have 2 nodes which is 2 to the maximum of, you may have less. At level 2 you already have 2 nodes. So, each can have 2 children. So, it is 4, that is 2 to the power 2 and so on. So, at level L the maximum that you can have is 2 to the power L number of nodes. So, given that if you look at a height h, then the maximum number of, so you will have to, what is the total number of nodes? N. At the maximum, let us say n less than equal to, the maximum is 1 at the root, then 2, then 2 square, and it goes on till you have the height h to the power h. And this as you know, this is a geometric progression. So, this is 2 to the power h plus 1 minus 1. So, the maximum number of nodes is bounded by 2 to the power h plus 1 minus 1, and also given the height, the number of nodes has to be at least at least one more than that, because that's n minus 1 edges. So, the height will be longest if every node has a single child, and therefore, it has to be n h plus 1, or n will have to be greater than or equal to h plus 1. So, given these two bounds, I can just do the algebra, write it differently, and say that h is maximum value of h can be n minus 1, which is the number of edges that you can have maximum, and the minimum of it is, if you just take the logarithm on this side, you will say log of n plus 1 ceiling, because it could be a non-integer number minus 1. And if I just look at the asymptotic approximation, then I will say that this is actually order log n and this is order n. So, the main result we get is height will always be less than equal to order n, which is obvious, and less obvious is it will be greater than equal to. So, the minimum height will always be order log n or more. If I have a KRE tree, this log, as you know, is taken with respect to 2, with 2 as base, because we are dealing with binary trees. If if it is a KRE tree, it will be taken in terms of log k. Right? Now, hash table is another concept where basically when you have to store the keys, you use a mathematical function to generate a number, typically an integer number, and use an array to store that particular value in that number, right. So, in this way it becomes much easier to find a lot of information. I will not go into explaining hash table here, this is just as a placeholder, because in module 44 later we are going to discuss in depth about hashing and its different applications. Now, let me move on to the main thing that we want to discuss here is the binary search tree. Now, again, from the study of the linear data structure, we found certain observations that binary search was the best possible way to find a key, that was of log n. But it has to be performed on a sorted array, and the moment you have array, you have a deletion insertion which is order n. So, that prevented us from getting this benefit of finding the key efficiently. On the linked list, on the other hand, insertion deletion is order 1, but the search becomes expensive. And in the linked list, just to remind, the insertion deletion can be order 1 because you do not need to move the data. In array, you need to move the data. In linked list, you just move the pointers, just references. So, you can do that in a number of constant reference movements, right. So, we want to use the nonlinearity to combine the benefits of both these. So, how do we do that? Let us say, just conceptually think that the data is in an array and it is sorted. Once it is sorted, then for any key during a search, we know the order in which the elements may be checked. For example, we first check the middle element of the array. So, the middle element splits it into left subarray and right subarray. What we can conceptualize that the entire array is a tree rooted in the middle element, and the left subtree is a left subarray is a left subtree, and right subarray is a right subtree. And if we progress recursively, we have a binary search tree. So, I will just illustrate through an example. Consider a data set having 7 data elements. I have purposefully chosen 7 not to get into fractions. So, they are sorted here, and this is the middle element. So, no matter what is your key, this is where you will do the first search, right? And I put that as a root here of the tree. Then these form my left subarray, these form my right subarray, left subarray, right subarray, left subtree, right subtree. Right? Now, once I have done the first, then I will either decide to compare with L, the element at L, or at R, no one else, right. So, these are the two subroots of the roots of the left subtree and the right subtree. So, the second will be L or R. Then what is next? If I did L, then I will either look at LL or I look at LR, either this or this, the two other sub arrays and sub trees. Or if I had done R, I will look at either RL or RR. So the way we do structured binary search, necessarily written out in terms of a tree, organizes in this way, so that we get, and we just need to keep on recurring. So what we get as a result is what is formally defined as a binary search tree. So what is a binary search tree? Where it has a node representing, every node has a value and possibly up to 2 children. So I have a value x here in the root, such that its left subtree, all values in the left subtree is less than that, each node. Please note this point. I have often seen in interviews that people forget this each node part. They just say that the root of the left subtree has to be less than x. That will be completely wrong, as you have seen, because the whole left sub array is less than the middle element. So each node in this, all y, will have to be less than x. And all on the right subtree, all y will have to be greater than that. If that satisfies at every node, then we have a binary search tree, exactly as we constructed from the binary search. So let's say, let us keep on inserting now to build this BST. Let us, no pun intended, but let me insert an elephant. So E is the first. Now L, where should L go? L is greater than E. So it must occur on the right subarray or the right subtree. So I add it as the right child. Then this P, where should it go? So what I do is, every time I have to, suppose I have to search for P, I have to insert P, I check for P in the array, and where it is expected, I will insert it. So P is greater than E comes on the right side, greater than L comes on the right side, so it becomes the right child of L. Then I have H, I search with E, it is greater, I compare with L, so I compare with E, it is greater, so I compare with L, it is lower, so it is on the left side, it does not exist, I add it here. Then I add A, it is smaller than E, so I add it as a left child. So it just goes on, it's as simple as that. Similarly, then I add N, because N is greater than E, I go to the right, greater than N, L, go to the right, less than P, go to the left, do it here. And finally T, which is greater than all of E, L, P. And this is, I have the binary search tree corresponding to elephant. Now, please note that this is not unique. You can see one very major difference than the earlier one is, in the earlier one, the left subtree and the right subtree had the same number of nodes. Well, that is because I chose 7. But even without that, they can always be made comparable. Whereas here, the left subtree has only 1, whereas the right subtree has 5. And this is a condition which we will say is a condition of being unbalanced, which is not a good thing to have, right? We will see that. Now, how do you search? As I said, it's very simple. You start with the root, compare. If it is equal, you say you have found the key. If it is less, you go to the left child. If it is more, go to the right child. And again, do that same thing. So, to look for So, to look for H, you compare with E, it is greater, you go to the right child. Compare with L, it is less, you go to the left child. Compare with H, it is equal. So, you say, I have got this node, return that pointer. If you are say looking for Q, you will, let's say you are looking for Q, greater than E, you come to L, greater than L, you come to P, greater than P, you come to T, less than T, there is no child. So, you declare that Q is not there in your data structure, the search fails. So, that is simply how the things go. So, now the question is, how many, given a key, given any arbitrary key k, say, how many comparisons and node traversals would you need? What is the extreme that can happen? For example, if you look at A can be found in 2 comparisons, H can be found in 3 comparisons, L can be found in 2 comparisons, P can be found in 3 comparisons. So you can always say that it is basically the level of the node plus 1, right? Because that path you will have to traverse. So what will be the worst? The worst will be when you do not get it. So anything, say B, C, D, will fail after 2 comparisons, because they will be expected after this A. Right? Then anything which is, say, if I have F, where will it be expected? Here. If I have G, it will be expected here. If I have I, it will be expected here. If I have J, it will be expected here, and so on. These all will need 3. Right? But when we did Q, it was expected at this point. So it is 1, 2, 3, 4, level is 4. So it level is 3, so you need 4 comparisons. Right? So basically, the maximum that you can get is the maximum of this expression, which is basically H plus 1 comparisons that you can need when the key does not exist and is expected as a child of the leaf node which has the longest path from the root. 2 things. One is it is not there, because if it is there, then it will require sum less. You can always have something which is not there. And what will maximize the level? If you have the longest path from the root. And what is the longest path from the root? Length of the longest path from the root is the height of the tree. So you will require H plus 1. So we can say that you in general require order H comparisons. So if H is less, the tree is good. If H is more, the tree is bad. As simple as that. And we have already noted that H has bounds. So given this, the searching of a key in the binary search tree is order H, the height of the key tree. The worst case will happen when all our nodes are like this, so that your height itself is n minus 1. So necessarily your search time would become worst in the order n. And what is the good, the best that you can have? When at every node you have subtrees which are of the same size, like you did in the binary search. The subtrees are always of the same size. So if that happens, then the height, the bound on the height is log n. So if the bound on the height is log n, all keys can be found in log n. And with the added advantage that all that you needed to do for insert or delete, so what happens on insert? You do a search plus insert. You first find out where it should be. If it is not there, then you insert. Now search is basically order log n, and this actual insertion is manipulating pointers, which is order 1. Same thing will happen with delete. So it's not only that with this, if I can keep the subtrees of almost the same size, then at every node, that is what is balancing. Then the binary search tree could give me the search, the insert, the delete, everything in order log n time, which is much better than which I could do in any of the linear data structure. So that is the basic advantage. Now if you broadly compare, this is the schematic of what we have discussed in this previous module and this module, and I have given a just a pointwise comparison that linear has a direct arrangement, whereas nonlinear has hierarchical arrangement. Linear naturally has a single level, nonlinear has multiple level. Linear is easier, nonlinear is more difficult to implement. Data elements in linear can be traversed in one way, whereas data elements in a nonlinear structure can be traversed in multiple ways to linearize it. You can do a depth first traversal, breadth first traversal, in order, post order, pre order, and so on. If you are not familiar, please look up your book on the algorithms and get familiar. We are going to need all of them and the examples. So with this, I conclude with a comparative chart of complexities of different operations: access, search, insertion, and deletion. In the average case as well as in the worst case, you can see that the colors mean green means absolutely the best, yellow means kind of the worst, and this yellowish green means something in between, which we are trying to look at. So here, when we were in the linear, we do not have any data structure which has only green or only greenish yellow. So that was a basic contention, but if you look at binary search tree, we have all greenish yellow in the average case. The worst case is still bad. So we'll have to make sure that we don't hit the worst case. But there are trees, there are nonlinear data structures that we are going to discuss later on, where like red-black tree, like B tree, these are going to discuss in subsequent modules, where you will see that no matter whether it's an average case or worst case, no matter which operation you are doing, everything is order log n, and that's the best that we can get. And the good thing is there is no space overrated for most of them. All of them use the order n number of spaces. So with that, I conclude this module. Thank you very much for your attention, and we will meet in the next module.